Hello students, congratulations for completing chapter 15 on halogen derivatives. It's one of the most difficult and important chapter in H2. So next we are going to move on to chapter 16 on hydroxy compounds. Hydroxy compounds is not a very difficult chapter, except that there are certain things you need to remember, like some of these reactions, for example, the oxidation to carbonyl compounds and carboxylic acid, the dehydration to alkenes, the acid-metal reaction with sodium to give you the respective hydroxides, as well as you probably need to know the difference between the mild oxidation. So for example, you need to know that certain conditions will give you aldehydes from primary alcohol. Certain condition you will get carboxylic acid and the difference in the oxidizing agent being used. Okay, so it is also in this chapter that you get to learn a very special functional group with a certain structural features. I think it's written here. So this particular structural features will give you a positive iodoform test, otherwise known as Tri-iodomethane test. Okay, so I will not speak too much on this. Later on, when we are discussing it, you will be able to see it for yourself. Okay, so I'm just going to move on straight to the introduction. So alcohols generally are compounds with the OH functional group. So I think there is a need maybe to distinguish a little bit between a group and a functional group. So for alcohols, when we call it a functional group, the R group that is bonded to the OH, the R group is an alkyl group. So we call the whole compound having the alcohol functional group. Hydroxyl, right, or hydroxy, right, is not a functional group. Hydroxy is simply a group. Why do we want to make such differentiation? So for example, carboxylic acids. Okay, I know I'm jump starting again, but let's say we have carboxylic acid. Carboxylic acid is actually made up of two groups. Okay, the first group is what we call the carbonyl group. Next, it's called the hydroxy group. So the combination of a carbonyl group directly bonded to a OH, this whole combination, right, we call it the carboxylic acid functional group. So there is a difference between a group and a functional group. So maybe it's good for you to know the difference right at the beginning. Don't really need to memorize any of these things. Just along the way, pay special attention to it as you study or as you listen to me during tutorials. That should be more than okay. Okay, so the most common alcohols you know it's actually found in beverages known as ethanol. So normally we just call it alcohols in general, but the one in our alcoholic drinks, right, is actually ethanol. Okay, and then of course you have menthol present in peppermint oil. Okay, so the OH group can also be directly bonded to a phenol ring. So if it's simply C6H5OH, we call it phenol. Okay, then you can have other substituent pattern on your phenol ring. So for example, you have this female sex hormone known as estradiol, right? Okay, so we move on to something which you are also quite familiar with from halogen derivative. That is the classification of alcohols. So we begin with a primary alcohol. So everything else is the same. Remember that in halogen derivative, I mentioned to you that there are two ways to decide on whether is the halogen derivative primary, secondary, or tertiary. It is the same case as alcohols. So if you have one alkyl group, we call it primary. Two alkyl group, secondary. Three alkyl group, tertiary. If you choose to look at it from the perspective of the alpha carbon, which is the C directly bonded to the OH, you can choose to look at it as having two H's being primary, one H being secondary, 0H being tertiary. That is perfectly fine as well. So it's really up to you how you want to classify it. Okay, then for nomenclature, similar to what we have in earlier topics. So one carbon, we have the prefix meth. Okay, 2 carbon F, 3 will be props, and then 4 will be bute. Yep. So for methane, its corresponding alcohol will then be methanol. Okay, so for ethane will be ethanol. For propane, it can either be propane 1-ol or propane 2-ol. Yeah. So there are different ways. There's another way of naming this. Instead of propane 1-ol, you can call it 1-propanol. Yeah. So it's really up to you how you want to name it. But propane 1-ol is the easier way to understand the naming. Right. Okay. So I'll just move on. I think the rest are pretty straightforward. Okay. So let's see. Okay, so basically you're just trying to locate the position of the alcohol. So whatever you name, so for example 5-ethyl 4-methyl octane 2-ol, right? How does this name come about? Basically, first you look at the longest chain. Okay, so we are looking at 2, 3, 4, 5, 6, 7, 8. So the longest chain contains 8 carbon. Yeah. So for the longest chain, the second position is the OH group. Yeah. So remember that hydroxy group or any functional group other than alkyl, right? They will have a greater priority. Yeah. So we always give them the lowest numbering when it comes to numbering of the carbons in the longest chain. Yeah. So the second carbon is hydroxyl or alcohols, OH, and then 3, 4. The fourth position is a methyl. Fifth position is an ethyl group. Yeah, so that's how we came up with the name 5-ethyl 4-methyl octane 2-ol. Yeah. Sometimes as a substituent, the OH is named as a hydroxy, especially when it comes after a structure with a higher priority functional group. So for example, in this particular name, right, we have a carboxylic acid over here. So the longest chain is 2, 3, 4. The longest chain is 4 carbon. Yeah. So 4 carbon we call it butanoic acid. You will learn it in the chapter on carboxylic acid derivatives. Okay. And then of course, because it has the larger priority, this particular carbon bearing the carboxylic acid functional group will take on carbon number 1, followed by 2, and then 3 and 4. So the third carbon contains an OH. Yeah. So it will be very strange to call it 3-ol butanoic acid. Yeah, it's just strange. So in this case, we call it 3-hydroxy butanoic acid. Yeah. Okay, so I think for those directly bonded to the benzene ring, you are aware that it's called phenol. Yeah, so any other substituent, we just name the position relative to the OH group. So in our case here, the one bonded to the OH take on position number 1. Yeah, so if we number it clockwise, that will be 2, 3, and 4. So second and fourth position is a nitro group, so we call it 2,4-dinitrophenol. Okay, yeah. So for exercise 1.1, we are supposed to name and classify the following alcohols and phenols. Okay, so we'll just do that very quickly. So first, I will highlight the longest carbon chain. Yeah, so that will be 1, 2, 3, 4. Yeah, so that will be a total of 4 carbon, and then I will start to number it. So that will be 1, 2, 3, 4. Okay, so in that case, the parents will be butane 2-ol. Okay, so this will be the parents. Yep, and we need to take a look at the substituent. Yep, so at the first position, we have a bromine, so that will be a bromo group. At the third position, we have 2 methyl group, so we will name this as 1 bromo, 3 dimethyl butane 2-ol. So yeah, it's a very long name, yeah, but no choice. Okay, and then this particular alcohol, right, is bonded to 2 alkyl groups. Okay, so it will be classified as a secondary alcohol. Okay, so next we look at this particular alcohol. Yeah, it seems to be a phenol, but it's not a phenol. Because if you actually sketch out the structure, it will look like this. So you have a benzene ring bonded to a C, and then this C is bonded to 2H and then an OH. Yeah, so this is a methanol derivative. Okay, so in that case, if you are going to look at it, it's more of one of the H of methanol is being substituted with a phenol group. Yeah, so with that, we will call this phenol methanol. Okay, and because there's only one alkyl group, we will classify this as a primary alcohol. Okay, yeah. Then next we will move on to phenol. Yeah, so this is pretty clear-cut phenol because the OH group is directly bonded to the phenol ring or the benzene ring. Okay, so this particular carbon number 1, and then 2, 3, 4, and 5. Okay, so in this case, we will take phenol to be the parent, so it's something phenol, right? And then second position is a methyl group, so we'll call it 2-methyl, and then fifth position is a bromo, so that will be 5-bromo. So you might call it 2-methyl 5-bromophenol. Yeah, but we have to number the substituent in alphabetical order. Yeah, so in this case, we'll name it as 5-bromo 2-methyl phenol. Okay, yeah, so that is how we name and classify the alcohols and phenols. So in this case, you can't exactly classify this alcohol, so we just call it a phenol. Yeah, some people will classify it as a tertiary alcohols because it doesn't have a alpha hydrogen. Yeah, but in general, we will call it phenol rather than a tertiary alcohols. Okay, then similar to halogen derivatives, alkanes, and even arenes, there exists isomerism in alcohols as well. So if you take a look at all this, okay, so alcohols, you can have chain and position isomerism as well as enantiomerism. Yeah, so if you recall what exactly is chain isomerism, yeah, so chain isomerism, right, it's referring to, for example, we have the longest chain here, so the longest chain over here is 4 carbon. Okay, so of course, one of the alkyl can actually branch, one of the methyl group can branch, and then we can get something like this. Yeah, so this is when we say that the A and B are example of chain isomers, or I mean in general they exhibit structural isomerism. Yeah, but structural isomerism is actually an old term. Yeah, so you have to think about what is the new term that you have learned. Yeah, okay, the new term you have learned is called constitutional isomerism. Yeah, but structural isomerism, if you name it, is still allowed. Yeah, so one of the subcategory of constitutional isomerism is chain isomerism. Okay, and of course, for this particular isomer, if I can actually shift the position of the OH group to the second position, then we will call it, we will say that the OH, this unknown exhibits position isomerism with respect to A. Okay, and then of course I can branch further to something like this. Yeah, then in this case A, B, and E exhibits chain isomerism. Yeah, okay, then C and D are examples of enantiomeric pair. Of course, when it's being drawn in this particular manner, it might be a little bit difficult for you to realize that they are enantiomeric pair. Yeah, so one way for you to recognize it is simply directly draw the mirror image. Yeah, so if I have C here, okay, so with a OH group and a H, I can easily draw a mirror image like this. Okay, and then I can flip it over. When I flip it over, this is what I'll get. Yeah, can you try to imagine it? Yeah, when you flip it over, this is what you get. Yeah, so in that sense, we know that C and D exhibits what we call enantiomerism. Okay, then okay, it's an empty page, so we'll move on to functional group isomerism. Yeah, so well, one of the things you need to take note of is that when we have an alcohol, right, we can actually we can actually swap the H and another alkyl group. Yeah, so for example, butane 1-ol, right, what I'm going to do now is, if I'm going to swap the H with this ethyl group, right, this is what I'm going to get. Yeah, so when we do that, we are actually having a new functional group known as an ether. Yeah, so that's why it's written here that ethers are constitutional isomers of alcohols. Yeah, so we are entering into a new functional group. Yeah, it's not an alcohol because it doesn't have the protonic hydrogen, but it is now what we call an ether. Okay, you notice that without the protonic hydrogen, intermolecular hydrogen bonding is not possible. So therefore, the boiling point is significantly lowered. But it is still relatively high due to the fact that it will be able to experience relatively significant instantaneous dipole-induced dipole interaction with its isomers, or I think otherwise we learn it as dispersion forces with its neighbors. Okay, yeah. Then moving on to the second section, right, we have physical properties. I don't think I need to spend a lot of time on physical properties because you would have experienced the bulk of it in chemical bonding. Okay, yeah. So basically, if you compare the alkane and the alcohol side by side, so for example, if I have one carbon, so for example we have methanol. Yeah, so methanol has the number of electrons in the molecules is 18, which is quite similar to that of ethane, right? Yeah, so you realize that the difference in boiling point is very, very different. So for example, ethane, the boiling point is negative 80 degrees Celsius, whereas methanol is 65 degrees Celsius. Yeah, then for propane, it's minus 42 degrees Celsius, but ethanol is 78 degrees Celsius. Yeah, so you can see that the presence of hydrogen bonding, right, significant hydrogen bonding, results in a large discrepancy between the boiling point of two molecules having similar relative molecular mass. Yeah, however, the difference starts to narrow when the electron cloud of the alkyl chain becomes larger and larger, because as the electron cloud of the alkyl chain becomes larger and larger, the probability of distorting the electron clouds of the non-polar groups become larger, and this distortion, right, there is a very huge chance of it leading to a relatively significant dipoles. Yeah, although it can be a very brief dipole. So this very, very brief dipole gives rise to very significant dispersion forces, or otherwise we call it instantaneous dipole induced dipole interaction. I think you can see this quite obvious, right? Say for example, to compare between methylbenzene and phenol, okay, and that between say a 6-carbon chain, for example hexane, and maybe pentanol. Okay, yeah. So well, I mean, you know, the difference between 69 and 138, it's probably about 70-ish degrees Celsius. Yeah, but you can see that as the alkyl chain become longer and longer, right, the nature of the hydrogen bonds, or the system having hydrogen bonding, right, is no longer as significant. Yeah, that can also be easily explained by the fact that as my alkyl chain gets longer, the probability of forming hydrogen bonds with neighboring molecules is lower. Yeah, because the presence of the flexible alkyl chain sort of disrupt the formation of the hydrogen bonds. Yeah, and of course another factor that adds in is because the electron cloud become larger and more polarizable, and similar reasonings as what I've mentioned earlier on. Okay, so yeah, I think I mentioned some of these things regarding hydrogen bonding, but usually the difference is really huge when the carbon chain is small. Okay, yeah, I think, yeah, second bullet point, I think I've also mentioned, as the size of the non-polar electron cloud gets larger, the dispersion forces becomes stronger. Okay, so phenol, I think you have a rigid benzene ring. Yeah, so that adds to the polarizability And of course, because, okay, another difference, right, you might notice, I mean, I thought I can just bring this in, is that, do you actually notice that, let's say I have something, having, say, a C6H5, of course having a methyl group, that's an additional number of carbon, but if you look at the total MR, right, it is actually relatively similar to, say, C6H14. If you compare the two, right, okay, you notice that the difference in boiling point is quite huge. So one of them you have 69 degrees Celsius, the other one 111. You might be wondering why, right? Yeah, because the rigidity of the system, right, does play a part in the system or the non-polar groups forming stronger and more significant dispersion forces. Yeah, I mean, you can always imagine that, let's say you have a very flexible LQ chain with a lot of carbon single bond that is free to rotate, then the probability of, you know, like of fixing the electron cloud in a certain shape actually gets distorted, or this particular shape keep changing over time, and this ever-changing shape, right, will actually result in a not very well-defined kind of dispersion forces. Yeah, like it's like not very strong in any particular direction, although it's still quite significant. Yeah, that is different if I have a phenol ring that is rigid. You have a ring system, it cannot undergo any free bond rotation except, say, between the ring and, let's say, the CH3. Yeah, then in that case it's able to form very significant dispersion forces between molecules. Yeah, so one thing you might want to take note of from here, right, is that if I provide the ring with some form of rigidity, or if I simply just convert it from a straight chain to a ring with a certain extent of rigidness, right, the boiling point will actually increase. Yeah, so you can just go through some of the materials. I mean, just go online, Google some of the boiling point, and you will see the difference. Of course, solubility in water, I think we have done a similar tutorial question in chemical bonding. Okay, so the alcohols with a shorter LQ chain, they tend to be quite soluble in water because the hydrogen bonding form is usually enough to overcome both the hydrogen bonding between the alcohol molecules as well as the dispersion forces between the LQ chain. However, as the length of the LQ chain become longer and longer, so for example, in our case here, this is a hexyl chain, 3,6, yes, it's a hexyl chain, right? Yeah, then the dispersion forces become more and more significant. Yeah, so when the dispersion forces become more and more significant, right, then you realize that the heat evolved in the formation of hydrogen bonds between the protonic hydrogen and water is no longer enough to overcome the instantaneous dipole-induced dipole interaction between the non-polar chain, or you can say no longer enough to overcome the dispersion forces between the non-polar LQ chain. Yeah, because of that, then their solubility in water actually decreases quite significantly. Okay, with that, we'll move on to exercise 2.1. You are supposed to arrange ethanol, ethane, and ethane 1,2-diol in order of increasing boiling points. Explain your choices. Okay, so in this case, I think this is not too difficult. Yeah, because for ethane 1,2-diol, right, what we have is a structure which looks like this. So you have 2 carbon with 2 OHs. So in this case, I expect ethane 1,2-diol to form more significant hydrogen bonding between ethane 1,2-diol molecules as compared to that between ethanol molecules. Yeah, just because it has 2 OH group versus ethanol 1 OH group. So I would expect this to have a higher boiling point than ethanol. Yeah, so the more number of OH group you have, then it will lead on to a greater probability of forming more extensive hydrogen bonding and as well as stronger hydrogen bonding. Yeah, so in this case, ethanol will have a lower boiling point than ethane 1,2-diol. And then of course, ethane will have the lowest boiling point because ethane can't form hydrogen bonding. Yeah. Okay, yeah, so I'll just leave it as it is, because chemical bonding is a topic which we have covered right in the beginning of last year. Okay, so next, question 2, we have hexane 1-ol with a boiling point of 158 degrees Celsius. Then 3,3-dimethyl butane 2-ol has a boiling point of 120 degrees Celsius. So explain the difference. So first, I think the easiest way to do this question is to sketch the structure out. So for hexane 1-ol, you'll be 2, 3, 4, 5, 6. Okay, so like this. Okay, 3,3-dimethyl butane 2-ol will look like this. Okay, so we have a butyl group with an OH, and then at the third position we have 2 methyl group. Yeah, so you realize that both hexane 1-ol as well as 3,3-dimethyl butane 2-ol, right, they are isomers of each other. Okay, so both of them are isomers. Yeah, how do we know? We can just count the total number of carbon. So both have C6H14O. Okay, 0 degree of unsaturation as well. Yeah, so in that case, how do we compare both of them? Okay, so first of all, right, when you want to compare hydrogen bonding, both have the same number of OH group. Yeah, so in that case, I expect the hydrogen bonding between hexane 1-ol molecule versus that between 3,3-dimethyl butane 2-ol molecules to be relatively similar in strength, although maybe one is slightly, one can form hydrogen bonding slightly more easily. Yeah, but the difference here is due to the non-polar chain. So in this case, this is straight chain. Okay, the straight chain has a larger surface area as compared to the branched. Okay, so because it has a greater surface area, the probability of it being distorted is greater. Yeah, so I expect the dispersion forces between hexane 1-ol molecules to be stronger than that between 3,3-dimethyl butane 2-ol molecules. Yeah, so because the dispersion forces is stronger, I expect hexane 1-ol to have a higher boiling point as compared to that between 3,3-dimethyl butane 2-ol molecules. Okay, next we'll look at question 3. Okay, so for question 3, the table below shows the solubility of various alcohols in water. Explain the trend. Okay, so I think we have mentioned this earlier on, and you would have seen chemical bonding tutorial questions very similar to what was written here. Okay, so you notice that from 1 to 3 carbons alcohol, right, they are all miscible with water. Yeah, for butane 1-ol, the solubility is about 1.1 mole per dm cube, relatively high, but when we reach pentanol and beyond, right, it becomes more and more insoluble. Yeah, so to explain the trend, I think the main focus is really what we sort of mentioned over here. Okay, so we can say that as the number of alkyl chain increases from, let's say, 3 to 4 to 5 to 6, then the probability of forming stronger dispersion forces between the non-polar side chain become higher. Yeah, so basically non-polar chain, the longer it is, the greater the chance of it being distorted, and the greater chance of, the greater chance of it being distorted will also mean that the greater the probability which it can form stronger and more extensive instantaneous dipole-induced dipole interaction with neighboring alcohols. Yeah, of course with the neighboring non-polar side chain of the alcohols. If you want to be really specific, you should do that. Okay, so because of that, it leads to the fact that the hydrogen bonding, the OH group in the alcohol forms with water molecules does not release enough energy to overcome the instantaneous dipole-induced dipole interaction between the non-polar chain. Yeah, so because of that, you expect a drop in solubility. Yeah, exactly what we talked about earlier on. Yeah, if you remember another factor which we talked about, the longer the chain, it also means that the greater the probability of the long chain interfering the hydrogen bonding formed between the OH group and water. Yeah, so that can also be explained in your answer. Okay. Then finally, the last question for exercise 2.1, we have the structure of sucrose shown below. You're asked to predict the physical state and solubility of the compounds under standard condition. Okay, so number one is, if you just do a quick count across, you notice that sucrose has a lot of carbon. Okay, so let's see, you have about 6 carbon on the left, 4, 5, 6 carbon on the right, total of 12 carbon. A lot of OH, okay, a lot of OH. So if I just highlight the 1, 2, 3, 4, 5, 6, 7, 8, so many OH. Yeah, so because of that huge electron cloud, huge a number of OH, I expect it to be a solid. Okay, I expect it to be a solid state. And at the same time, am I expecting it to be soluble in water? Yes, I expect it to be very soluble in water because of the huge number of OH group present. Yeah, so number one is I expect sucrose to be a solid. Yeah, because number one, yes, rigid electron cloud. Number two, many OH. So rigid electron cloud means probability of forming stronger dispersion forces is higher. Many OH group. That also means that the extent of hydrogen bonds between sucrose molecules is quite large. And of course, not only is the hydrogen bonding extensive, it is also strong. Yeah, therefore I expect the heat in the surrounding at room temperature will not be significant enough to overcome the hydrogen bonds between sucrose molecules. So I expect it to remain as a solid, as what I mentioned earlier on. And then for the solubility in water, I think I have given my thoughts on that. Many OH group, so definitely the probability of forming extensive hydrogen bonds in water is very high. Right. Okay, so next we'll move on to section 3 on the preparation of alcohols. We will not be going into great details in the preparation of alcohols for very simple reasons. Because you have learned them in earlier topics such as alkenes, where you are able to obtain alcohol by the electrophilic addition of steam to alkenes. If you do recall, for mild oxidation of alkenes, you will be able to obtain diol as well. And then in the previous topic, under halogen derivatives, for example, if you are given 2-bromopropane, if you want to obtain the corresponding propane 2-ol, you can simply subject 2 bromopropanes to sodium hydroxide and you heat it under an appropriate condition. Okay, and then in the later topics, which is the next topic on carbonyl compounds, you will learn that the reduction of aldehydes and ketones using sodium boron hydride or lithium aluminum hydride dry ether will be able to give you the primary and secondary alcohol respectively. Yep, and then in topic 18 under carboxylic acids and derivatives, you learn that if I'm going to perform a reduction of carboxylic acids using lithium aluminum hydride dry ether, I will be able to obtain the primary alcohols. Yep, so with that, we will straight away jump into chemical properties and reactions of alcohols, which we think is a lot more important. Okay, so the reactivity of the OH group allows the alcohol to be versatile starting material. Yeah, for a very simple reason, of course, because the OH bond is polar, so delta minus delta plus, and you know that the protonic hydrogen can easily be lost. So if it's lost as a H+, then the alcohols will be converted into what we call an alkoxide. On its own, it can behave either as a nucleophile or as a base. Okay, then if I'm getting rid of the whole OH group, I'm able to get many other compounds. So for example, if I subject an alcohol to an appropriate condition, for example PBr3 or PCl3, we are able to get the corresponding bromide and chloride. Okay, yeah, so these are some of the examples which is shown over here. The kind of reaction where the CO bond is cleaved is known as nucleophilic substitution, but you do not need to know the mechanism. Okay, so one little thing about this particular chapter is that mechanism is not required. Yeah, but you can be guided to draw the mechanism in an assessment question if you are being asked for. Yeah, so not to worry so much. As long as you get enough practice, that should be fine. Okay, so 4.1 under combustion, I think needs no introduction, so I'll just skip. Okay, and then of course 4.2 acid-base reactions of alcohols and phenols. If you recall from the earlier topic on acid-base equilibrium, you should be kind of aware that the greater the extent of ionization, that sort of implies that the corresponding conjugate base is more stabilized. Yeah, so in a learning objective that's explicitly mentioned, you are supposed to explain, or you need to know how to explain the relative acidity of water, phenol, and ethanol in aqueous medium. Okay, you're supposed to compare them. Okay, so as I mentioned, it's related to the conjugate stability of the conjugate base. So regarding the acidity of alcohols, you notice that alcohols are slightly weaker acids as compared to water. Again, as I mentioned, these are all relative. So when we will term alcohol as neutral, we won't call alcohol an acid. Okay, but if the right condition is around, so for example, if I have a very strong base, then of course an alcohol can potentially lose its protonic hydrogens. Yeah, okay, so the extent of ionization of the alcohol in water is so low that there isn't even enough H plus present to cause the blue litmus to turn red. Okay, so a very simple explanation, if you just compare directly with the water, right, is that you notice that the O minus, okay, is directly bonded to an electron donating ethyl group. So the electron donating ethyl group, right, will intensify the negative charge at the oxides, and in that situation destabilize the ethoxide anion more than that of OH minus. So in that case, we will say that the extent of ionization for ethanol as compared to water is actually lower. Okay, yeah. A very important idea which I thought I should make brief mention is that the strength of the alkyl chain does not exactly have an impact on the acidity. So that means that the longer it is, it doesn't mean that it is significantly less or more acidic. It doesn't mean that if I have a super long chain, that acts as a super powerful donating group. Okay, there's no such thing. Okay, although the acid could be stronger or weaker due to other reasons, but the reasons is not due to the fact that because the longer the chain is, the greater the donating ability. So please do take note of this. Okay, yeah. So if you take a look at this particular small sections, right, you notice that say if I have an alcohol with electron withdrawing CF3 group, right? Yeah. So it's able to withdraw the electron density away from the conjugate base of nonylfluoro-tertiary butyl alcohol via the sigma bonding framework. Yeah. Because fluorine is more electronegative than carbon, so with respect to electronegativity difference, is able to withdraw electron density away from the sigma bonding framework, binding up all the carbons and of course the O's. So the corresponding conjugate base, if it loses the H plus with an O minus here, the withdrawing effect will help to stabilize the negative charge. So to make the negative charge less negative, so that it has a lesser tendency to grab back the H plus. Yeah, of course, as compared to say methanol. Okay, then for 2-methylpropane 2-ol, does it mean that the alkyl group, because I have a bigger alkyl group, it is a stronger electron donating group? So the answer is no, it is not a stronger electron donating group in that sense. So when you compare the pKa's, right, it has got to do with the extent of stabilization of the conjugate base in the alcohol medium. Yeah, so when this loses a H plus, so when it loses a H plus, we are able to get this tertiary butoxide anion. So the tertiary butoxide anion, right, will form a less extensive hydrogen bonds with the corresponding alcohols in the medium. Yeah, so because of that, the O minus is more available to say coordinate back the H plus. So this make it a weaker acid as compared to say ethanol. Okay, So do not just count the number of alkyl groups bonded to the alpha carbon. Yeah, because the whole group is one alkyl group. Yeah, just take note of this. Okay. The distance of the electron withdrawing group from the alkoxide center of the conjugate base, of course, it's important. So for example, if we have 2-chloropropane-2-ol at the second position, it will exert a stronger electron withdrawing effect via the sigma bonding framework as compared to 3-chloropropane-2-ol. Remember, all the comparison, right, is related to when the H is lost as a H+. Okay, which means the corresponding conjugate base. Yeah, do take note of this. You do not compare directly. Normally, we'll compare, if you want to compare whether an acid is a stronger acid than the other corresponding acid, we will compare the stability of the conjugate base. Okay, so this is a very important concept which I need all of you to be aware of. Yeah, so the other topic which you're going to have extensive discussion on concept like this is on bases. Yeah, so in general, just in general for H2, when you want to compare whether acid A is stronger or acid B is stronger, you compare their conjugate base stability. Yeah, but if you want to compare whether base C is stronger or base D, you compare the availability of the lone pairs of electrons on the corresponding nitrogen group. Okay, we'll talk more about that when we reach amines. Okay, so we have exercise 4.1 now. You're supposed to arrange the alcohols in order of increasing acid strength. Okay, so you notice that I have 3 alcohols over here. So this is a normal propane 1-ol. Okay, so this is a propane 1-ol with the chloro group at the second position, and then the other one is propane 1-ol with the chloro group at the alpha carbon. Yeah, okay. So again, similar reasoning. If they were to lose their H+, their protonic hydrogen in this case, so I'm just going to erase it. So in some sense, we are going to compare the stability of the conjugate base, okay? Yeah, so if you look at propane 1 oxide, it simply has electron donating alkyl groups. So this helps to intensify the negative charge at the O. So when I compare across the 3, this must be the weakest acid. So strongest base, weakest acid. Okay, so maybe I can say destabilize. Okay, I can just say strongest conjugate base. Strongest conjugate base. Okay, then on the other hand, the one with the chloro group at the alpha carbon will be able to exert a stronger electron withdrawing inductive effect on the O- as compared to that in the second position, or otherwise we call it the beta carbon. Okay, yeah, because remember, electron withdrawing group is related to the distance the group is from the negatively charged center. Yeah, so in this case, this will be the most stabilized, so it will be the weakest conjugate base. So this is okay, this is the medium one. Yeah, so when we arrange them, okay, then this will be the strongest acid, followed by this, and then followed by propane 1-ol. Okay, so it will be in this particular order. Yeah, so next we'll move on to the acidity of phenol. Yeah, if I didn't mention earlier on, I'm going to mention this now. I think it will be a very good thing if you guys can remember the pKa of a benchmark reagent. Okay, so my suggestion is to remember that of phenol. Okay, so phenol pK is 10. Okay, so please remember phenol. Remember for ethanol as well, pKa 16. Okay, the other compound which I really would like all of you to remember is simply a carboxylic acid such as ethanoic acid. I know you may have recalled from my acid-base equilibrium lecture that when I say the pK of carboxylic acid, ethanoic acid in this case is always 4.76, right? Yeah. but we can just approximate it to 5. Yeah, the reason why I need you to know the pK of these few benchmarks, right, is because in the future, right, when you are given question and you are given comparison, say if I have an electron withdrawing group or donating group placed into one of the either phenol or ethanoic acid, etc., right, you are able to make some good comparison and some good referencing. Yeah, but of course it's really up to you whether you want to remember the values. It's not too difficult to remember. Yeah, but it's good to remember them so that it's easy for discussion. Yeah. Okay, so in our case here, phenol, you notice it's 1 million times a stronger acid as compared to ethanol. Why is that the case? Well, because the lone pairs of electrons, right, I think it's drawn very nicely here for you. The lone pairs of electrons on the oxide after the H plus is being lost, right, is partially delocalized into the phenol ring. Okay, yeah, so the O minus is spread out into the benzene ring. So negative charge is spread out into the benzene ring. But some of the misconceptions students often have is that that means that each carbon will take 1/7 of the negative charge. The answer is no. Actually, the bulk of the negative charge is still at the oxygen. Yeah, but it is just that some of its electron density is now spread out into the benzene ring. Why is it that the bulk of the electron density is still at the oxide? The reason is oxygen is a lot more electronegative as compared to carbon. So it doesn't make sense to agree that the negative charge gets spread out equally into the phenol ring. So it's a wrong concept. Yeah. And I can also take this opportunity to explain to you why is it that ethanoic acid is a significantly stronger acid as compared to phenol. That's because for ethanoic acid, after losing a proton, right, the ethanoic anion has a negative charge spread out equally between the two oxygen. Yeah, do take note that this is really an oxygen here. Yeah, so the two oxygen, right, can really take on half the charge because oxygen and oxygen have the same electronegativity value and they are at a similar distance from the carbon-carbon. Okay, this particular diagram showcases the delocalization of the negative charge on oxygen into the phenol ring by drawing the appropriate resonance structures. Your friends doing H3 should be able to explain this a little bit more to you, but for today's context, I'm not going to explain to you. Yeah, basically, the drawing of all these resonance structures, right, simply showcase to you how the negative charge is delocalized into the benzene ring. Yeah, so the drawing of resonance structures is sort of a way to compensate the lack of a proper representation of a delocalized electron cloud on paper. Yes, okay, so yeah, if you are interested in this, you can explore some of the H3 content which I put up, or you can read more from the textbooks. Okay, yeah. Then moving on, right, similar to alcohols, the presence of electron withdrawing groups will also allow the negative charge to be more stabilized and more spread out. So for example, 2,4,6-trichlorophenol, the pK value is 7.6, so that makes it around 1,000 times more acidic as compared to phenol. Okay, and then of course 4-chloro, and it's a bit lower than phenol. Yeah, because of the presence of only one electron withdrawing chloro groups. Okay, yeah. But another thing which may sort of surprise students, I'm not sure, is that if I have an electron donating group, the strength of the phenolic OH group will decrease. Why is that the case? Yeah, because an electron donating group increases the electron density of the benzene ring. So the increase in electron density will result in a negative charge on the phenoxide, right, being less likely to be delocalized into the benzene ring. So because it is less likely to delocalize, or it has a lower incentive to delocalize, it makes the negative charge more negative as compared to that of phenoxide. So making it a weaker acid. Yeah, so in that case, if I have electron donating alkyl groups, it makes the phenol less acidic than the phenol. The substituted phenol less acidic than a normal phenol. If I have an electron withdrawing group, substituted to a phenol, then it is more acidic as compared to that of a phenol. Yeah, if you remember the little thing which I mentioned to you in earlier on, I mean maybe in JC1, yeah, you notice that the idea of electron withdrawing and donating group is actually very easy to understand at the H2 level for chemistry if you simply just look at how spread out the charge is. So for example, if my center here, okay, I just call it a center, if the center here is negatively charged or has a lot of electron densities, if it is bonded to, say, an electron donating group, for example, then it will make the negatively charged center more negative, right? Correct? So therefore, you can conclude that the donating group will decrease the stability, okay, of the species. Yeah. So on the other hand, if I have an electron withdrawing group, okay, bonded to this particular center, it will increase the stability of the species because it makes the negative charge less negative. Yeah. So on the other hand, the same concept can be applied. If I have a center here that is positive, okay, then if I have an electron donating group bonded to this center, it makes the center less positive. So it stabilizes the center. Think of it as a carbocation. You know, like we say that primary carbocation is less stable than secondary carbocation, which is also less stable than a tertiary carbocation. Why is that the case? Because the increase in electron donating group helps to stabilize the carbocationic center. Okay, if we have an electron withdrawing group, what's going to happen? Okay, the electron withdrawing group will destabilize the center, so it will decrease stability. Okay, so donating group will increase stability. Okay, why will withdrawing group decrease stability? Because your center is already positively charged. Then the withdrawing group will withdraw more electron densities away from the center, then obviously destabilizing it. Yeah, so if you are able to look at withdrawing and donating groups from this particular perspective, then I think it will make your life quite easy for organic chem. Okay, with that, we'll move on to exercise 4.2. You are asked to arrange the following phenols in order of acid strength. 1 is the most acidic, 5 is the least acidic. Yeah, so simply using the same idea which we discussed earlier on. So let me use yellow highlighter to highlight those electron withdrawing groups. So we have NO2 here, and then we have NO2 here. So obviously, for the most acidic phenol, this is definitely the most acidic because it is bonded to 3 electron withdrawing nitro group. Then this is the second most acidic because it's bonded to 1 electron withdrawing nitro group. Okay, and then of course phenol is the benchmark, so it's number 3. Yeah, and then I'm going to use a purple highlighter to highlight donating groups. So we have 1 donating group in the 4th phenol and 2 donating group in the 1st phenol. So in that case, the 4th phenol will be the second least acidic, and then of course the phenol bonded to 2-methyl group, where the electron donating group will decrease the incentive for the negative charge on the phenoxide to be delocalized into the phenol ring. It will be the least acidic. Okay, so I hope you find exercise 4.2 quite intuitive. Okay, the next section we're going to discuss is 4.2.3, where we are going to talk about acid metal reaction with sodium. Yeah, sodium is often used. Okay, yeah, so we will term this as a redox reaction for a very simple reason, because the sodium oxidation state increases from 0 to +1, okay, in Na+. And then the oxidation states of hydrogen here decreases from +1 to 0 in hydrogen gas. Yeah, so in fact, this is actually a redox reaction. Contrary to popular beliefs, right, the ethoxy group, nothing has changed. So it did not undergo oxidation or reduction. It is simply a single electron transfer between the sodium and the protonic hydrogen. Okay, so please take note of the condition. Sodium room temperature. Yeah, usually you simply just cut a piece of sodium and then you just dump it into the alcohol to produce ethoxide. Okay, so you will observe slow effervescence of hydrogen gas. You can easily test it with a burning split. Okay, the next part, if I'm not wrong, over in your notes, there's a typo, so please correct it. Okay, it should be phenol. Okay, with sodium metal, and then you end up with sodium phenoxide and half H2. So similar idea. And because phenol is more acidic as compared to ethanol, right, you expect rapid effervescence of hydrogen gas. Okay, so there's a slight difference in the kinetics. Okay, yeah. Then next, we'll be discussing acid-base reaction with sodium hydroxide, sorry. Yeah, so phenol is acidic enough to react with bases such as sodium hydroxide or sodium or potassium hydroxide. Usually we can use the aqueous version, means aqueous sodium hydroxide or aqueous potassium hydroxide. Yeah, occasionally we can also use solid sodium hydroxide and solid potassium hydroxide. Sometimes it might be better. Okay, yeah. And phenol has relatively low solubility in water because it has a large phenyl ring, yeah, which is non-polar. Yeah, so the ID or the dispersion forces between the phenyl ring is quite strong. So in that case, the hydrogen bonds formed between the phenolic OH and water is insufficient. Okay, I mean the energy release is insufficient to overcome the dispersion forces between the non-polar electron cloud in the phenyl ring. Yeah, but when I input sodium hydroxide, it's a different ballgame. Yeah, because this particular species form, which is known as phenoxide, right, is able to form stronger ion dipole interaction with water. Yeah, so it makes it soluble. So you will be able to get a homogeneous colorless solution. Okay, so the cloudy solution you get when you put phenol in the water is because of its poor solubility. So please remember that. So the observation here will be cloudy mixture dissolved to give a colorless homogeneous solution. Yeah. However, right, this should not be used as a test. Okay, so this method should not be used as a test for phenol. Should not be used as a test for phenol. Yeah, remember that. Okay, so for phenol, we have a separate test which is better. Alcohols, in most cases, do not react with sodium hydroxide. Yeah, but over here, right, please take note of the very important word here. It's aqueous sodium hydroxide that doesn't react with the alcohols. Okay, so you may just want to incorporate AQ here. Yeah. However, right, I think I've shared with some of you in the classroom. If I am able to, let's say, have pure ethanol, so let's say I have 95% to 100% ethanol, okay, and I input pellets of potassium hydroxide and sodium hydroxide, for example. So let's say this is solid NaOH, okay, in pellet form. Okay, if you just dissolve them directly in pure ethanol or neat ethanol, yes, then in this case you are able to allow the alcohols to undergo the necessary redox reaction to produce the ethoxide. Yeah, so this is possible. Yeah, so this is quite generic. Yeah, so what they are trying to say here is that if I just have say some alcohol, so ethanol, and then I just pour a normal concentration of sodium hydroxide into it, I'm not going to expect any acid-base reaction. Yeah, but if I'm going to use close to 100% ethanol, let's say 90-95%, and then I put in pellets or solid state sodium hydroxide or potassium hydroxide, I will expect a reaction to take place. Okay, an acid metal reaction will take place. For 4.3, right, this is not required in your syllabus. The mechanism is not required, which is the nucleophilic substitution. Yeah. Basically, if I just give you a very simple idea, why is replacing OH group known as nucleophilic substitution, right? Yeah. Basically, what we are doing here is that, or what exactly is happening is that the OH group is a very poor leaving group for a very simple reason. Because the OH group, right, if it leaves, it will leave as hydroxide anion. But hydroxide is a relatively strong nucleophile, and of course it's a strong base as well. So it makes it reluctant to leave. Yeah, so whenever we want to substitute OH for something else, right, we will first need to convert the OH into a good leaving group. And then subsequently, right, the corresponding halide, in this case it could be chloride, it could be bromide, or iodide, will then be able to replace the newly formed group, which is a good leaving group. Yeah, so this is exactly what's happening here, but we will not be discussing the mechanism. Okay, so if you are interested, you can read some of the undergraduate textbook for more information. Okay, so over here we have a reaction with hydrochloric acid, but this has to be concentrated hydrochloric acid. So please take note of it. It has to be concentrated hydrochloric acid. Yeah. Okay, and then what's going to happen is that basically the H plus will protonate the OH group, and then your OH will leave as water. Okay, and that's how after your OH leaves as water, the chloride will then substitute for the OH, and you get this particular tertiary chloro group. Okay, solution will turn cloudy. That's an observation. Yeah. However, if we want to do it for primary and secondary alcohol, right, we won't be reacting with concentrated HCl alone. Okay, we will have to incorporate anhydrous zinc chloride as well to act as a catalyst. Okay, so in this case, the solution will turn cloudy maybe more slowly as compared to if you use a tertiary alcohols. Okay, but of course, in order to accelerate the reaction, we'll be using zinc chloride as the catalyst. Okay, the brief mechanism is sort of mentioned here, but again, I probably don't want most of you to go into details. If you wish to, you can read about it, but I have already briefly mentioned to you the mechanics of it. So first, it involved the protonation of the OH group to become OH2 plus. So the oxygen gains a +1 formal charge, and then after that it's lost as water, and then of course after that the chloride will then come in to attack the carbocationic carbon. Okay, so this particular reaction, right, it has a legacy name. It's known as the Lucas test. It's used to distinguish between primary, secondary, and tertiary alcohols. Okay, so basically the reagents and conditions, corn HCl and zinc chloride. Yeah, so for tertiary, cloudiness appears immediately. For secondary, within 5 minutes, okay, at room temperature. And then primary, no cloudiness unless you warm it. Yeah, remember, warming always sort of allow the system to have more energy, so that they probably have enough energy to overcome the activation barrier. Okay, then another way to replace the OH is to subject the alcohols to concentrated HBr. Okay, or in some cases, you should be able to generate HBr in situ. So a mixture of sodium bromide and corn sulfuric acid will be able to generate HBr in situ. The meaning of in situ means it's being generated fresh. Yeah, which is very important. If you wish to know the chemical equation, right, it is simply like this. So you have H2SO4 concentrated, which is a liquid, plus NaBr. Okay, so what's going to happen is that one of the protonic hydrogen will be lost, so I'm going to generate HBr gas. Okay, and in the process, I'm going to get sodium hydrogen sulfates. Okay, which in this case will be sort of solvated in corn acid. So I think I'll just write it as a solid here. Yeah, but it will be kind of solvated in the corn acid in that sense. Okay, yeah, so that's how the reaction with sodium bromide works. Remember, you either use sodium bromide in corn sulfuric acid so as to generate HBr gas in situ, or you will use concentrated hydrobromic acid. Okay, and then next we are going to discuss the popular reaction, which is to use phosphorus halides. Okay, so there's a difference between phosphorus trichloride and phosphorus pentachloride. Yeah, just one all of you to remember. Phosphorus trichloride is actually a liquid. Phosphorus pent chloride is a solid. Yeah, so it depends on the kind of reaction you want to do. You can decide which one you want to handle. Yeah, so these are the three sets of condition you need, or reaction you need, in order to get the corresponding OH to be substituted with the corresponding halogen. Yeah, so only phosphorus trichloride can be used. Phosphorus tribromide is not very stable, so they have to be prepared in situ, as well as phosphorus triiodide. Yeah, but PCl3 is okay, stable enough for it to exist. Yeah, so the reason why we have phosphorus and Br2 here is really to produce PBr3 in situ. Same case goes for phosphorus and iodine. Okay, PCl5 works as well. Your seniors or many generations of students, they like to use PCl5 for a very simple reason, because I can allow the reaction to occur at room temperature, whereas for PCl3 or for PBr3, all this I need to heat it. PCl3 actually no need to heat as well, so I think the room temperature condition works. Okay, yep. And then the use of PCl5 is often a good distinguishing test for alcohols. Yeah, provided that carboxylic acid is present. You will normally observe white dense film of HCl. So do take note of this. Okay, another common reagent, if let's say you do not like to use PCl5 or PCl3, you can use thionyl chloride, SOCl2. Yeah, however, SOCl2 needs to be accompanied with warming. Okay, and of course, in the course of the reaction, you generate two acidic gases. Okay, HCl and SO2, and SO2 is also a reducing gas. Yeah, but if you okay, so both of these reactions are what we call entropy driven, because they produces gaseous molecules. But of course, for thionyl chloride, you produce more gaseous molecules. Yeah, so because of that, it's easier to push the reaction to completion. Okay, so that's something you need to take note of, especially when you allow the gas to escape and then be absorbed into a base sink. Okay, so that would be a very good way for you to perform the reaction. Some students might ask, does thionyl bromide exist? Yes, but needs to be prepared as well, because it's not so stable. Okay. Phenol is resistance towards nucleophilic substitution, again for similar reasons as halogenoarenes. Yeah, so because the lone pairs of electrons of oxygen is partially delocalized in the benzene ring, so strengthen the CO bond, and at the same time, the nucleophile will be repelled away due to the pi electron club. Okay, so similar reasons. I don't think I want to go into details as well. Dehydration, we kind of mentioned a little bit of it in the alkenes chapter, like how do we produce alkenes. Yeah, so again, the way to produce alkene, we need not start with alcohols. We can start with halogenoalkanes. Yeah, they can undergo what we call dehalohydrogenation, or if you remember what I told you from the topic on halogen derivative, the reaction is known as beta elimination. Yeah, so same case for alcohols, we can allow the system to undergo dehydration, or otherwise known as elimination of water, if we want to produce alkene. Yeah, please remember the different conditions or different sets of reagents and conditions. If you decide to use corn sulfuric acid, please ensure you have excess corn sulfuric acid. You need to heat. You need to drive the water out. Yeah. Another way is to use H3PO4. Okay. Of course, one of the other condition, right, we call it the dry condition, is to use aluminum oxide and heat it. Okay, so this is probably a better method if, let's say, you don't want the system to come in contact with any form of liquids. Yeah, sometimes concentrated phosphoric acid is a better alternative as compared to sulfuric acids. Okay, the reason being sulfuric acid could be an oxidizing agent as well. So in the course of reaction, if let's say there are other gases such as HBr, all this being given out. I mean, not in this case. I know in this case there's no HBr. But in reaction where you do produce some halide, hydrogen halide gases, right, then concentrated sulfuric acid may result in the oxidation of that particular gas to the corresponding halogens. Okay, that's something you need to take note of. And then for our dehydration here, we are going to produce a mixture of alkenes. So similarly, the more substituted the alkene is, then the more stable is the product. Yeah, so in general, we'll try to draw an alkene with a greater degree of substitution. But that is not to say the mono or di-substituted products do not exist. Okay, similarly, right, in elimination, we call it beta elimination. Dehydration is also one form of beta elimination because when you remove the OH as water, the extra hydrogen comes from the beta hydrogen that is bonded to the alpha carbon, or rather that is the beta hydrogen is bonded to the beta carbon. So remember that this is beta, this is alpha, so this is beta H, right? So the H is bonded to the carbon adjacent to the alpha carbon. Okay, so you can say that the H is bonded to the carbon that is directly bonded to the carbon bonded to the OH, but that is a mouthful. So that is why it is good to understand some of the terminology which chemists love to use. That is alpha, beta. Okay, then certain kind of alcohols cannot undergo dehydration for a very simple reason, because there is no beta hydrogen. So because of that, dehydration cannot take place. Okay, then yeah, so phenol can undergo dehydration. So this is probably something you need to take note of. Okay, for exercise 4.3, we have 1-methyl cyclohexanol. So you are asked to give structures of all products formed when 1-methyl cyclohexanol reacts with each of the following reagents. So if it reacts with PCl5, okay, so I'm going to get the OH group being replaced by Cl. Okay. Okay, so something like this. Sodium bromide corn sulfuric acid, so it generates HBr in C2. So I'm going to get the OH group being replaced by Br. Okay, concentrated sulfuric acid in excess, so I'm going to expect dehydration. Okay, so my dehydration products. Okay, so let us check out how many beta H are there. Okay, so there is a beta H over here. There is also a beta H over here. Okay, so there are two beta H's. So one of the products should be like this. Okay, and of course the other products will be like this. Okay, so these are the two products I'm expecting. Of course, the thermodynamic products will be this. Yeah, because it is tetra substituted. Okay. Next, alcohols can undergo what we call condensation reaction. Okay, so what exactly do we mean by condensation reaction? Okay, so basically in the course of reaction, a small molecule evolves. Okay, so in this case, if I allow ester to be formed, then H2O will be eliminated from carboxylic acid and alcohols. Yeah, so this is known as condensation reaction, where H2O or HCl is being produced. Okay, so I need you to be aware of this reaction, and usually the catalyst is concentrated sulfuric acid. Okay, this is needed to accelerate the reaction. And the key reasons, which I probably don't want to mention too deeply here, right? The presence of concentrated sulfuric acid is really to protonate the carbonyl oxygen to make this carbonyl carbon more electron deficient. Okay, the more electron deficient is your carbonyl carbon, the more susceptible it will be towards nucleophilic attack by a weak nucleophile such as an alcohol. Okay, yeah. Then going to move on to this part. Unlike alcohol, phenol cannot react with carboxylic acid in condensation reaction. Yeah, the very simple reason is, remember that for phenol, right, the lone pairs of electrons is partially delocalized into the benzene ring. So this partial delocalization, right, makes the lone pair less available for nucleophilic attack at the carbonyl oxygen. Yeah. So because of that, ester will not be formed between a carboxylic acid and a phenol. If you want the ester to be formed, you have to adjust the condition. Okay. For condensation reaction with acyl chloride, yeah, remember earlier on, over here, we mentioned that in order for condensation reaction to occur between alcohols and carboxylic acid, you will need concentrated sulfuric acid to serve as the catalyst. How does it serve as the catalyst? It helps to protonate the carbonyl oxygen. In the process of protonating, the carbonyl oxygen will gain the +1 charge, and this makes the carbonyl carbon more electron deficient and therefore more susceptible to nucleophilic attack by a weak nucleophile. Okay. On the other hand, right, acyl chloride is the more reactive version of carboxylic acid. Yeah. So this is the more inverted comma reactive version of a carboxylic acid. Yeah. So because of this reaction can be done at room temperature. Even a weak nucleophile such as alcohol can be used. And acyl chloride, if you have not seen it before, I think you should Google and check how most of the acyl chloride looks like. They tend to be liquids, but if you open it up, especially in very humid Singapore, right, it will just fumes in the air to give you HCl gas, and itself gets hydrolyzed to give you carboxylic acid. Yeah. Other than that, acyl chloride, they are very good reagents to be used to produce ester, because I don't need to heat, I don't need a catalyst, due to the fact that the acyl chloride carbonyl carbon is highly susceptible to nucleophilic attack by even weak nucleophile. Okay, yeah. So remember earlier on, we made a very important point. We said that the lone pairs of electrons on phenol partially delocalize into the phenyl ring, so it makes it less available to nucleophilic attack carbonyl carbon, right? Yeah. But what if we want it to react nonetheless, right? In that case, we have to change the nature of the carbonyl carbon, and we need to change to an acyl chloride functional group. And because of that, I do not need to use any catalyst. I can simply just use phenol and acyl chloride, and then boom, they'll react. And in the process, white fumes of HCl is released. Yeah. So this two part tends to be confused by students, the reactivity between alcohols and phenol towards carboxylic acid and acyl chloride. So when in doubt, please come back to this particular page for revisions. Okay. Then in most cases, if we want an excellent use of the phenol ester, okay, we will not simply use phenol. We will simply convert the phenol into a stronger nucleophile, such as phenoxide. And then if you convert it into a stronger nucleophile, then it will be able to form ester more readily. Yeah, okay, so remember, the rates of reaction is also an important consideration even in normal laboratory work. Okay, then next we move on to the most important section, which is oxidation. You need to know the two differentiating reagents. One is potassium dichromate acidified with sulfuric acid, so that's number one. Number two is potassium permanganate acidified with sulfuric acid. Okay, so the product of the oxidation is largely dependent by the alcohols, but most importantly, in order for oxidation to take place, you need to have an alpha hydrogen. That means that the carbon directly bonded to the OH, right, must contain more than one H, or one H or more. Okay, or at least one H. Yeah. So for this reason, tertiary alcohols are usually not oxidized by the above reagents. I use the word usually not, but it happened before, sometimes when you try to do a lab work on the tertiary alcohols, it can be oxidized. How do you know? Because potassium permanganate changes color to brown. Okay, and phenol can also be oxidized if I'm going to use 1,4-dihydroxy phenol, which can undergo redox, but we'll deal with that later. Okay, so first of all, oxidation of primary alcohol. Yeah, so if we control the oxidation well, first product we're going to get is the aldehydes, and then if we subject the aldehyde to further oxidation, we'll get the carboxylic acid. Yeah, so remember that this is true only for primary alcohol. So only for primary alcohol you can get aldehydes. Yeah, because for secondary alcohol, straight away you go to ketones. Basically, secondary alcohol has one less H, so this is essentially an R group. So if I have an R group here, this will be what we call a ketone. Okay, if I want to get the ethanol, okay, I need to do something called controlled oxidation. Yeah, controlled oxidation can happen in most cases because remember that alcohols form extensive hydrogen bonding with itself and maybe in the aqueous medium, but ethanol doesn't form hydrogen bonds. So that means it can be distilled off quite easily if you solely want the aldehyde products. Yeah, but if you want the carboxylic acid product, then you just reflux for a longer period of time. Okay, then yeah, the distillation setup is given here. I think it needs no introduction. Water in must be over here, so that when the water flows in, over here is being filled with cold water. Okay, and then of course water out because the water gets warm up. Yeah, and potassium dichromate and alcohol needs to drop in, needs to put into a dropping funnel and be introduced to the system slowly. Okay, for the reaction to take place. Then you must always adjust your hot plate temperature. Okay, so that you do not let oxidation to become uncontrollable. Yeah. Okay, so this is the reagents and conditions you might want to remember. In fact, you should remember for the purpose of your exam. Yeah, so the reagents and conditions will be potassium dichromate acidified with H2SO4, heat with immediate distillation. Let me just underline this again. Immediate distillation. Yeah, because the aldehyde form is more volatile. Yeah, but please do not put in potassium permanganate with heat with immediate distillation. There's no such thing. So potassium permanganate is a stronger oxidizing agent than potassium dichromate. So it cannot stop at the aldehyde stage. Remember this. It cannot stop at the aldehyde stage. Okay, so if I want carboxylic acid, then it doesn't matter. I'll just reflux all the way. So once I reflux all the way, my final product is likely to be carboxylic acid and it is less volatile. Yeah. Okay, so in this case, this particular setup will be sufficient. Yeah. In that case, why is a reflux condenser still required? It's required because remember for reaction, right, we usually start off with alcohols, and then if we form the aldehydes, both of these are very volatile and they could diffuse away. Yeah, so we still need the reflux condenser in order to condense back the liquids. Okay, yeah, so potassium dichromate with sulfuric acid heats under reflux. So that's the difference. The earlier on one is heat with immediate distillation. This is heat under reflux. Yeah, so there's a difference, and this usually takes a slightly longer period of time. Okay. Oxidation with secondary alcohols. How does it work? Same thing. Yeah. So why can it be oxidized? Because it has alpha hydrogen over here. So this is the alpha hydrogen. Okay, so it can be oxidized. Yeah, but because it has two R group, right? So it will move. It can't reach carboxylic acid, obviously. So it will reach ketone, and that's it. Yeah, because ketone, remember from alkenes chapter, it is reluctant to be oxidized further. For a simple reason, because it doesn't have much activated hydrogen or activated CH bond. Yeah, I think earlier on I forgot to mention that oxidation often takes place because of activated CH bond, and the activated CH bond is due to the electron withdrawing inductive effect of the OH group onto the C. Yeah, so when the CH bond gets activated, it gets weakened. And when it gets weakened, it is more reducing. So if I put in an oxidizing agent, then oxygen might be inserted in between, and then this will lead on to further oxidation. Okay, so I probably need you to remember some of these relatively basic facts. Okay, I mean, one simple ideas I can present to you. Sorry if I backtrack a little bit. One simple idea I can present to you would be, for example, this particular primary alcohol. I'm just going to draw it in. Okay, OH. Remember that we say that the OH group will activate the CH bond towards oxidizing agent. That means that it makes the bond weaker and therefore more reducing, right? Yeah. So when I subject it to an oxidizing agent, the first product I'm expecting, right, is actually an oxygen insertion. So I'm going to get an OH here. Oops, sorry. Just going to get an OH here. Yep. And a carbon bonded to two OHs is actually not stable at all. So it will quickly lose the remaining group as water. Okay, so the two OH group, you are able to lose a water molecule. So where will the water molecule be lost? You reach here. So I'm just going to draw. So this will be lost as water, and this is indeed the water here. And then of course, because it's lost as water, right, this thing will become aldehyde. And once it becomes aldehyde, the CH bond gets further activated, and therefore there's oxygen that's inserted between the carbon and the H. Yeah, so that's how eventually you end up with a carboxylic acid. Yeah, so same idea for secondary alcohols. It's a similar idea. Yeah, so as oxygen is inserted between the carbon and H at the first instance. Yeah, so there's oxygen being inserted. Yeah, and then of course this whole portion is lost as H2O, and eventually you form the C double bond O, which is the carbonyl group. Okay, yeah. You might want to take note of the observation. So potassium dichromate will turn green when you subject the system to oxidation, or purple potassium permanganate will turn colorless due to the Mn2+. Okay, so oxidation can be used as a distinguishing test for primary, secondary, and tertiary alcohols. Okay, how can we use it as a distinguishing test? But before we discuss this distinguishing test, right, I would like to remind all of you that in simple chemical tests, you should not be using reflux and distillation. Okay, the test should be as simple as possible, less than 1 minute. If heating is involved, normally we'll heat it in a water bath. Okay, just remember that. Okay, so I will not discuss too much about this because I think when you are working on questions, then it will be a little bit more obvious. Yeah, but just off the top of my head, if I just want to talk about it super briefly, tertiary alcohol, because it doesn't contain any alpha hydrogen, it will not be oxidized. Okay, for primary and secondary alcohols, primary alcohol will be oxidized all the way to carboxylic acid, whereas secondary alcohol will be oxidized to a ketone. Yeah, so sometimes in order to distinguish between the two, you can't exactly distinguish a secondary alcohol from a primary alcohol because the final product, ketones or carboxylic acid, probably they are not so easy to be distinguished without adding additional reagent, of course, without doing a secondary test. Yeah, so in most cases, we will avoid doing secondary test. Yeah, so like what was mentioned here, if I want to distinguish between the ketones and the carboxylic acid, I will first need to perform a distillation to distill the ketone over, and then we test whether that is a ketone. Yeah, because ketone has lower boiling point as compared to carboxylic acid. Okay, yeah. Then I'm going to move on to exercise 4.4. We are supposed to draw the structures of the compounds formed by oxidation of each of the following compounds. Okay, so potassium dichromates, acidified potassium dichromates. Okay, so in this case, I'm going to get a ketone. Okay, yeah. Remember that the CC double bond will not be oxidized by potassium dichromate. If you recall from alkenes, only potassium permanganate will cause oxidative cleavage. Yeah, so if you forget about oxidative cleavage, basically, if I'm going to number my carbon, 1, 2, 3, 4, 5, 6, right? Carbon number 1 and 2, in our case here, will become carboxylic acid. Okay? Yeah, because the first product is actually an aldehyde, but aldehyde has an activated CH bond, so it will then be continuously oxidized to a carboxylic acid. Okay, so in this case, my products, I'm going to draw it out very quickly. Okay, so this is a carboxylic acid. Okay, so that's 1, then 6, 5, 4, 3, and then 2 will be a carboxylic acid. Oh, sorry. Oh, yes, sorry. What am I doing? Yeah, okay, so another carboxylic acid here. Okay, I hope that's fine. Then for parts B, potassium dichromate heat with immediate distillation, definitely no side chain oxidation. Why is that the case? Because I'm using potassium dichromate heat with immediate distillation. I'm going to get the aldehydes. Okay, but again, can I also mention, this might be questionable as well. Why? Because the phenol ring is quite huge, so whether it can be distilled over or whether it can be isolated as a solid, that I think needs further discussion. It's definitely not something which we can discuss very quickly here because a lot more information is required. Okay, potassium permanganate in H2SO4 acidified condition, it will produce the corresponding carboxylic acid. Okay, so the methyl group will be oxidized to carboxylic acid, and then this portion will undergo side chain oxidation as well, so to get the corresponding carboxylic acid. And of course, because the side chain contains 2 carbons, so I'm going to get a CO2 as well. Okay, so remember this, some of the basic ideas you learned earlier on. Okay, yeah. So I'm going to move on to the next section, which is on the iodoform test. So the iodoform is an old name for CHI3. The modern name or the IUPAC name is known as Tri-iodomethane. Why is it called Tri-iodomethane? Because it has a structure of methane, but 3 of the H is being replaced by iodine. Okay, so yeah, so this is the balance equation. Yeah, it has this particular structural features which I need you to remember. So basically, I have a CH3 here, bond and alpha hydrogen. Okay, I have another R group here. Okay, that particular R group can be H or it can be LQ. So the only primary alcohol which undergoes iodoform test is ethanol. Okay, the rest of the alcohols which are able to undergo iodoform test, right, are all secondary alcohol, because it is necessary that the R group, if it's not a H, then it is minimally an LQ group. So if it's an LQ group, then it has to be a secondary alcohol because the alpha carbon contains at least 1 H. Okay, there is a need for you to sort of remember how to write the balance equation. Yeah, so some students just remember it as 4, 6, 5, 5. Again, I wouldn't recommend that. I would recommend all of you to learn how to derive the balance equation, which I'm going to teach you over here. Let me see if I have any blank space. Yeah, I'm going to just teach you how to balance the redox equation, okay? So that you do not need to, I mean, if in exam you forget, at least you don't anyhow write down something. Okay, so first I will write down the formula of the generic alcohols. Yeah, of course, with the said functional group. So we have a C, we have a H, we have a OH, okay, we have a CH3, and then of course we have an R group. So over for our this particular discussion, right, can we just assume that it is a carbon-based group? So this is just carbon-based. Yeah. Why didn't we want the R to be a H? Well, I mean, I think I want to make the balance equation as generic as possible. So, when R is a H, it's only one out of the many, many cases. So I think in my discussion, I prefer it to be a little bit more generic so that it will help you to understand more things. Okay, so yeah. So with that, if you remember how to calculate oxidation states by assuming a perfect ionic model. Okay, so first of all, I'm going to write the carbon out, then with a H, okay, and then with an O. I'm not going to draw out the whole structure here, okay, so with a CH3, okay, so CH3, I think I can write them out, CH3, 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 and then another carbon here. Okay, so now I'm going to draw the boundaries. Okay, carbon is more electronegative than H. Okay, so I'm just going to draw a boundary like this. Carbon, carbon, no difference. Okay, carbon, carbon, no difference. Oxygen more electronegative than oxygen more electronegative than carbon, so we take all the electrons. Okay, so in that case, this particular carbon has an oxidation state of 0. Okay, and then the other carbon has an oxidation state of -3. Okay, so I'll just write down in purple. So this is 0 and this is -3. Okay, I'm going to write out the half equation. Okay, then you get to know how it can be balanced. And then the products, remember, is CHI3, right? So I'm just going to write out CHI3. So CHI. Okay, plus R. Yeah, because the CHI3 actually comes from CH3 over here. Yeah, so the other parts will become carboxylic anion. Okay, I'm going to write down the oxidation state as well. So for this particular carboxylic anion, the carbon rate is actually +3. Okay, so for this carbon here, again, assume perfect ionic model. So iodine more electronegative, blah, 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 then it then become +2. Yeah. So if you take a look at the whole thing, right? What is the change in oxidation state? So it's from 0 to +3. Okay, sorry, I'll try again. From 0 to +3. Okay, and then from -3 to +2. Okay, so in this case, it loses 3 electrons, and then over here it loses 5 electrons. So the net is 8 electrons being lost. Okay, you might want to pause for a while and think about it. Okay, is it agreeable that 8 electrons is lost at the end of the day? Okay, so with that, I'm going to erase this part because I think it's easier, it's less messy. Okay, so now 8 electrons being lost, right? Remember in iodoform tests, we use iodine, right? So the 8 electron that is being lost, it should be gained by iodine, right? So it will be gained by the iodine. But each iodine can only gain 2 electrons. So in order to gain 8 electrons, I will need 4 iodine. And in this case, I'm going to get 8I minus. Okay, so we are quite there already, because if you look at the balance equation, it's time we can do some cancellation. Okay, yeah. So the first thing we need to do is to add up these two half equations, so that the electrons gets cancelled away. Okay, so this electron will get cancelled away, and then very, very briefly, I'm just going to write plus 4i2 here. Okay, so because I wrote plus 4i2, I'm going to cancel away the 4i2. And then the 8i minus, right? Okay, 3 of it will go to CHI3, or rather the CHI3 equivalent, which is CH plus. Okay, but you can just count it as CHI3 lah. And then so therefore we are left with 5. Okay, and then of course this 5 will come to here, so I'm going to write plus 5 iodide over here. Okay, so the final thing you need to do is to balance the charge. So if you look at the total charge on the left hand side, it's 0. The total charge on the right hand side, if you do a quick calculation, is -1 minus 5, so it's -6. So therefore, I need to add 6OH minus on the left. Okay, and then after you added 6OH minus, the final thing you need to do is to balance the O and H using H2O. Okay, and some students found that relatively challenging, but it can actually be done quite fast by just doing a quick count. Okay, so how do we do the quick count? Okay, so just very simply, what is the number of H on the left hand side? Of course, I need to dismiss the R lah. Okay, so over here we have 6, 7, 8, 9, 10, 11. Okay, so we have 11 H's on the left hand side. Okay, and oxygen, we have 7 oxygen, so 6 plus 1 is 7, so we have 7 O's. Okay, right, and then on the right hand side we have 1 H and 2 O's. And then what do you notice? If I simply just do a cancellation, so 11H I cancel, here left with 10H, 2 O's I cancel, left with 5 O's. Yeah, so there's a balance of 10H and 5 O's I need to balance on the right hand side. So therefore, I'm going to get 5H2O. Yeah, so now let's compare the two formula. Do you realize it's the same? I mean the balance equation, sorry. It's the same, right? So it's 4, 6, 5, 5. Yeah, so that's how we do the balance equation for the iodoform test. I know it's very long, it's very complicated. I mean, not complicated, it's tedious. But if you become very proficient and very sharp at doing it, right, then you realize that it's not as difficult as it sounds. Okay, yeah. I'm just going to move on quite quickly. I think I mentioned this. All are secondary alcohols except ethanol, which is primary. Note that this reaction involved the breaking of the CC bond. Yes, I think you can see that. Basically, the CH3 is being removed, and eventually the CH3 become CHI3. I think you guys can see that. Equation you need, or the condition, is iodine in alkaline medium, and then you warm it. Okay, final product is the carboxylate anion. And because you lose a carbon, this kind of reaction is known as step-down reaction. Okay, so if you gain a carbon, it's known as step-up. When do you gain a carbon? Remember, ethanolic KCN heat under reflux with halogen derivative, we increase the carbon count by 1. So that's an example of gaining 1 carbon. Okay, yep. I will leave this particular background information to you because the methyl alcohol group is not the only group which gives rise to positive iodoform test. There's also another group known as the methyl ketone group. Yeah, but in general for iodoform test, right, it does involve a mild oxidation. Okay, so to some extent the alcohol does get oxidized to give us a methyl ketone first before further oxidation takes place. Yeah, this is due to the activation of the alpha CH group, but I will not go into details on the mechanism because earlier on I think I briefly mentioned that as well. Okay, then next we will look at exercise 4.5. Which of the following alcohols will give a positive tri-iodomethane test? So again, I'm just going to draw out or highlight the methyl alcohol feature, so it's over here. Okay, 2 is a tertiary alcohol, so it's out. Okay, 2 is out as well because it's primary. Okay, this contains the methyl alcohol. Okay, so in that case, the answer will be 4 and 1. Okay, yeah. Question 2. Chemical tests were carried out on 4 organic compounds labeled A, B, C, D. The compounds are ethanol. Okay, so maybe I draw it out. Ethanol, propane 1-ol, 2-methyl propane 2-ol. So this is propane 2-ol, 2-OH like that. And then cyclohexene. Alright, but not necessarily in that order. Okay, so observation for each of them is as follow. You add sodium, effervescence, B, no effervescence, So therefore, I can correspond B to cyclohexene. Yeah. Can I do that? Well, I mean, I can do that because number one, it doesn't react with sodium, so that means that it does not have any protonic hydrogens. Yeah, so B has to be the one without protonic hydrogen, so therefore it's cyclohexene. And then negative test for the rest. Okay. Then I'll look at a differentiating one, which is the iodoform test. Yeah, so amongst all these here, right, only ethanol give me iodoform test, so therefore C is ethanol. Okay, so in that case, I will put C as ethanol and then B as cyclohexene. So I'll just draw it out. Okay, and then I'll look at potassium dichromate acidified heats. You notice that only the remaining primary alcohol can be oxidized, tertiary alcohol cannot oxidize, so remain orange. So A must be tertiary alcohol. Okay, so this is A. Okay, and then B I've identified, C, and then of course donkey will be propane 1-ol. Okay, so that's how we can do this quite easily. Yeah, and of course quite confidently as well. Yeah, so if you are in doubts or if there's still certain concepts you are not very clear about, please go back to the relevant timestamp for the relevant section so that you can click and review them again. Okay, next we're going to look at other reactions of phenol. Okay, so of course phenol undergoes electrophilic substitution, but phenol has something really interesting because it has an OH group directly bonded to the phenol ring. The OH group is what we call sigma withdrawing and pi donating. Yeah, so this is something which I often mention in the class. I don't know whether you can recall. So I'm just going to briefly mention it over here. So what do we really mean when we say sigma withdrawing and pi donating? Okay, so first of all, I'm going to draw in the pi electron cloud, okay, on the benzene ring. And then I'm going to draw an OH group here. Okay, so the OH group contains lone pairs of electrons. Because the OH group, the oxygen, contains 2 lone pairs, right? So it has a choice of being sp3 or sp2 hybridized. Yeah, so under normal context, you will think that it is sp3 hybridized. Yeah, because 4 electron domains or 4 electron groups. Yeah, so normally we'll think that it's sp3 hybridized. Yeah, but you need to also understand that because it is next to a pi system, one of the lone pair prefer to overlap partially with it, so that the whole structure can take on a lower electronic energy. So this partial delocalization, right, will necessitate the lone pairs of electrons on O to be found in the p orbital. Yeah, so therefore the O will be sp2 hybridized instead. So one of the lone pair is in the sp2 hybrid orbital, the other one is in the p orbital. This allows the partial delocalization of the lone pairs of electrons onto the benzene ring possible. Yeah, so this partial delocalization, right, is what we call a pi effect. Yeah, so the partial delocalization of the lone pairs of electrons on oxygen into the phenol ring will increase the electron density in the benzene ring. Yeah, so that makes it more susceptible to electrophilic substitution. Yeah, however, oxygen is more electronegative than carbon. So the OH group, okay, will be able to result in an electron withdrawing inductive effect on the sigma bonding framework. Yeah, so normally we say that OH group is sigma withdrawing and pi donating. Yeah, however, right, if there are 2 competing effects, usually in most cases the pi effect will win, because the pi effect involves a direct delocalization of the pi electron cloud onto the phenol ring. So it makes it maybe the effect is actually stronger as compared to a sigma withdrawing effect. Yeah, so because of that, then as the net effect is that OH group is electron donating instead of electron withdrawing. Yeah, the same argument can be said of NH2. Yeah, so because of that, right, if you simply add aqueous bromine to it, it can undergo tribromination without even adding a Lewis acid catalyst. And this is also the case for NH2 in phenolamine. Okay, yeah. Then for electrophilic substitution with nitric acids, if you simply use dilute nitric acid, you might get mono-substituted products, like what we have shown here. Okay, so this is for dilute nitric acid, like really dilute. Then if I want to get tri-substituted products, then I have to use concentrated nitric acid. Okay, yeah, so normally I will get a pale yellow liquid because the presence of nitro group will result in a yellow kind of coloration. Yeah, because of the I mean, in H3, the students learn about the pi to pi star gap, which I think I will not go into further discussion over here. Okay, then we move on to the tribromination. Yeah, so the electrophilic substitution of bromine will easily result in tribromination. And one of the key things which students tend to write wrongly is the byproduct is HBr. Okay, some students will not remember the byproduct is HBr because they forgot that the H here is being substituted. Yeah, so remember the H is being substituted, and because of the pi donating nature of the OH group, right, I do not need a Lewis acid to generate the electrophile for electrophilic substitution take place. So you will be able to generate its own electrophile. Yeah, so no Lewis acid catalyst is needed. Okay, yeah, so the observation will be yellow-orange solution decolorized. The yellow-orange solution is actually your aqueous bromine. Okay, if you want monobromination, you have to do it at really low temperature, and maybe you shouldn't use a polar solvent such as water. Yeah, normally we'll simply just use liquid bromine or bromine dissolved in CCl4. Yeah, remember that a low temperature is required, so low temperature. Then usually in such a reaction, if you want to carry out in large scale, right, because hydrogen bromide gas is given off, it will be good to direct the gas and bubble it into sodium hydroxide solution, so as number one, not to pollute the environment, to make, I mean, because the presence of the acidic gas will destroy I mean the surface of the fume hood or this, so it's good to bubble the gas into sodium hydroxide solution. Okay, and then the last bit of it, very famous distinguishing test for phenol, it is to add neutral iron 3 chloride. I think this portion is also needs to be corrected, so I think on your notes, this highlighted portion which I mentioned, you probably want to correct the typos. Okay, so remember we are using neutral iron 3 chloride, so we'll observe purple coloration. Yeah, so this is a very obvious test for phenol. Yeah, something which I need all of you to take note of. Yeah, you'll end up with a purple complex when the phenol coordinates to the iron 3. Okay, so this is a distinguishing test for the presence of phenolic group in organic compound. Okay, so I think that's it for alcohols. Yeah, so this is the last page. Right, so again, as I said, if there's any portion of the notes you are not familiar with, please look at the timestamp, go back to the relevant sections. If not, then the next time around I'm going to see you will be on chapter 17 on carbonyl compounds. Okay, so thank you very much.